The particle in a box system is a relatively easy system to solve, and it also allows us to extend our understanding to higher dimensions. So now I want you to consider a three-dimensional box. So before we had a box that was just one-dimensional, but now if we have a three-dimensional box, that might be a box that fills some volume. And now we're going to insist that the wave function hit an infinite potential whenever it hits one of these walls of this three-dimensional box, which means that those are all effectively boundary conditions for this particular system. So we might write these axes as x and y and z going in the upward direction, just for example. So I'm going to arbitrarily set these limits as Lx for x and 0 to Ly for y and 0 to Lz for z. All right, and so the wave function will exist in this box subject to these boundary conditions, but the boundary conditions really are a result of the infinite wall that appears at those walls. All right, so when we write the Hamiltonian for the particle in a box, in the 3D box, it will be minus h bar squared over 2m, but now we'll have components in all three of those dimensions. So I'll go ahead and put the psi in, psi squared x plus d squared psi dy squared plus d squared psi dz squared. And this implicitly has a psi over here. All right, and so all of these are going to be equal then to the energy times psi. Now there's a couple of things that we can work into this. Okay, one is we can write this wave function as the product of parts that correspond to x, y, and z. So this is a little bit like separation of variables, except it's maybe even easier perhaps, because in this case we're basically just having derivatives with respect to each of those individual variables. This derivative, this first derivative, only affects the first part here. The second one only affects the second part, and the third derivative affects only the third part. So we end up with our action of our Hamiltonian on this wave function looking something like this. We'll have negative h bar squared over 2m, and then in each of these things I'll have y of y, z of z, and then the second derivative of x with respect to x. And then I'll have x of x and z of z times the second derivative of the y part with respect to y. And x of x and y of y times the second derivative of the z part with respect to z. And all of this will then be equal to e times x of x, y of y, and z of z. Now if I divide through by this wave function, I'll end up with three terms now that will be a little bit simpler, not much, but a little bit. 1 over x of x, d squared x dx squared, plus 1 over y of y, d squared y dy squared, and 1 over z of z times dz squared, d squared z of dz squared is equal to just our energy. Okay, since I have a term that depends only on x, a term that depends only on y, and a term that depends only on z, I can now break this e down into a part that comes from x, a part that comes from y, and a part that comes from z, because these are all completely separated from one another. So a variation in x will not affect whatever's going on here or here, and likewise the same for a variation in y won't affect the x part of the z part, and a variation in z won't affect the y part of the x part. So it means that we can then kind of separate this into effectively three Schrodinger equations. So I'll have minus h bar squared over 2m and times 1 over x of x, d squared x dx squared equals ex. So now when I multiply both sides by x of x, I'll end up with the effective Schrodinger equation in the x direction of minus h bar squared over 2m d squared x dx squared equals e sub x, x of x. All right, so we can see that this is identical to the 1D particle in a box. All right, which means that essentially this more complicated problem really isn't more complicated at all. We can separate it into three parts, x, y, and z, and so that means that we can solve each of these individually, and we already know the solutions. So we know that for this x part, that our wave functions, so I'll call this y sub x n, or maybe I should just leave it as x sub n of x, is going to be equal to, and I can even include the normalization constant if I wish, it's going to be 2 over L sub x sine n pi x over L sub x. And I'm going to have similar expressions for y and z. So for example, y of y sub n, maybe I'll make that y sub ny and x sub nx, so I better put an index on these integers. So that would be equal to the square root of 2 over ly sine of ny pi y over ly. And z would be square root of 2 over lz sine nz pi z over lz. So now when I put all this together, my overall wave function, and my overall wave function now has three of these quantum numbers. And it's going to have a compound normalization constant, so it'll be 8 over Lx, Ly, Lz, and then I'll have three sine terms, nx pi x over L sub x, sine of ny pi y over L sub y, and sine of nz pi z over L sub z. Okay, I'm going to go on to the next page to talk about the energies of this particular solution, but we'll see that those will turn out to be fairly easy to generate as well. So once again, for the 1D particle in a box, we had that the energies were given by n squared h squared over 8m L squared. So now I can generalize this for E sub x, n, would be n sub x squared h squared over 8m L sub x squared. E sub y, n sub y, I should probably put a little x over there too, is equal to n sub y squared h squared over 8m L sub y squared. And E sub z, n sub z, would be n sub z squared h squared over 8m Lz squared. So my total energies, again as functions of all three of these integers, parameters, can be written like this. But now I'm going to have ny squared over ly squared plus nx squared, let's do x first, ny squared over ly squared, and nz squared over lz squared. So these now are my solutions, my eigenvalues for the Schrödinger equation for this three-dimensional particle in a box. Now, this is fairly straightforward and I hope has been easy to follow, but I wanted to raise one possibility just to illustrate a new point, and that is, what if we have Lx is equal to Ly is equal to Lz, and let's just set them all equal to L. So now when I write the energy levels down for this particle in a three-dimensional box, and again I'll specify that it's got all three of these quantum numbers. Okay, now all of these terms that are in the denominator can be brought out front. So I'll have h squared over 8m L squared, and now I simply have nx squared plus ny squared plus nz squared. All right, this is for a cubic box now in which the particle is. So this actually now opens up the possibility that, let's suppose I want to specify my states by giving the values of these three numbers. So this could be, for example, 1, 1, 2. So it would be 1 plus 1 plus 2 squared is 4, so that's 6. So this would have an energy of 6h squared over 8ml squared, or 3h squared over 4ml squared. But notice that if I had instead the state 1, 2, 1 or 2, 1, 1, I would get the same energy. Okay, what this is telling us is that these three states that I've indicated, 1, 1, 2, 1, 2, 1, and 2, 1, 1, these are degenerate states. And whenever we have a built-in symmetry, as we do here, it's a cubic box, this is basically a result of the system symmetry. And we find that in general, when we have symmetry like this in a system, we're going to have some degeneracy that results from that system. Now we can also have something called accidental degeneracy. And this could happen even if we have three different lengths for the sides of the box. So, for example, even this case could give rise to accidental degeneracy, but it's not built in, if you will, as a prefactor based purely on the symmetry of the system. We'll get a chance to explore all of these concepts a little bit more as they apply to molecular and atomic systems, but it's good to be aware that this is a possibility where we have more than one eigenstate that has the same energy, yet those eigenstates are distinct from one another and they would look different if we looked at those eigenfunctions.